Thank you, Doreen. And also thank you for allowing me to come here to this very nice workshop. It's my first time here and I really love it. And it's a spontaneous opportunity that this talk is happening. So I'm also excited about this. I will be talking about something similar to what we heard already yesterday by Stephen. But it's a bit of a different approach to it, a bit of a different perspective about numerical integration of loop amplitudes in momentum space. So let me, interrupt me anytime if you have questions or so. Let me start with a short motivation. So why am I doing what I'm doing? So this is all aimed, of course, at predictions for hadron colliders. And there we usually start with the factorization formula that states that if you want to calculate the cross-section, we have to integrate over phase space, over the Parton distribution functions, over some observable, and the amplitude squared. And the amplitude itself is an integral over the loop degrees of freedom. Now this integral, the cross-section integral, is typically performed numerically with Monte Carlo event generators, but then the loop integrations in the amplitude is typically performed analytically. And this talk is about doing this exact integration numerically. And why would we want to do that? Because I think you might think that it's much better to do it analytically. We do it once and we have it once and for all. And that only makes sense if you look at it in the current state of these calculations, because at leading and next to leading order, these analytical techniques, they have so matured that these calculations are now considered automated. But then at next to leading order, there are some building blocks that are not as well understood. In particular, the calculation of two-loop amplitudes. Of course, many successful two-loop calculations have already been done. So what I'm saying here is kind of like what the problems are at the frontier, or what I think the problems are at the frontier of these calculations, in particular for 2 to 3 processes, and with many mass scales, massive propagators, or massive final states. And then the IBP reduction typically becomes so difficult to handle for the best computers. And even if we can do this IBP reduction, and we end up with master integrals, then they still have to be solved, either analytically. Like I'm not going to say too much here because I've not actually worked with these tools, but that we know that that there are problems either in the analytical solving of these differential equations, or other ways, or numerical integrations, for example, over a Feynman parameter space that we heard of, that this might not be like the most efficient approach, and so on. So what I'm talking about is supposed to sidestep these problems. So the question is, can we sidestep it with numerical integration? And then another challenge in these next to leading order calculations are the real emission contributions. Why is that? Because of the infrared singularities that we have to do something about. This we can do with like subtraction or slicing methods, but these become increasingly involved when we have more collinear directions, for instance. And then these tools or these approaches become difficult to handle. And numerical integration of loop amplitudes would give you a framework, at least, to treat the loop and the phase space integration similarly, because you do the phase space integration and the loop integration numerically. So you can even hope to locally cancel these infrared divergent regions locally directly in your integration space. And what this could look like, just kind of as a teaser. Oh, sorry about that. Could be this picture. So we know that if we calculate the cross-section, it's proportional to the imaginary part of the forward scattering amplitude, which with the optical theorem, we can represent like this, where we now see exactly why it's difficult to handle these contributions, which are virtual and real emission contributions in the same framework. And that's because kind of the phase space that we integrate over here is a 2-body phase space. And here for the real emission contributions is a 3-body phase space. So there are different integration spaces. So how would we like align these different singular regions locally? And one way out of this, which is kind of motivating what's supposed to come, is that these contributions can be, if we know how to cut loops into trees, which is basically what I'm doing here. So if I cut this loop here into trees, then all these contributions, they start to look the same. They start to look like diagrams with the same number of cuts. And that suggests that their integration spaces are actually the same. And if they are the same, then we can hope to cancel these singular regions. And because we already know that at least at integrated level, this contribution is infrared finite, because that's really the statement of the KLN theorem. Okay, so so much about the motivation. So what happens if you want to integrate a loop integral numerically? The first kind of obvious problem is that loop integrals are typically divergent in 4 dimensions. So we have to do something about this. So we have to get rid of the UV and infrared singularities. And in momentum space, we can do this with local UV counter terms or local infrared counter terms. Or if one follows this approach to combine real and virtual corrections under the same integral sign, then we don't have to worry about divergences anyways, because everything is supposed to be finite in 4 dimensions. So with these subtractions, one can render loop integrals finite. At this point, I should also mention that, of course, sector decomposition achieves a similar thing by extracting these singularities. I'm not going to mention any more about this, just refer to Stephen's talk. But even then, the numerical integration becomes difficult, although we have an integral that's finite in 4 dimensions. And for this, we can look at a very simple, let's say, a 1-loop triangle diagram. And why is this integral difficult to evaluate numerically? And that's because these propagators, the denominator can vanish, which makes the integrand blow up. So we have poles in the integration domain, and that makes numerical integration problematic. But thanks to the causal prescription, we are protected from these poles. But this is like an analytic regulator. How do we regulate these integrals in for numerical integration? And that's kind of the main question. Everything that I'm about to show is basically how to resolve this problem, how to get rid of this I epsilon prescription so that we end up with an integral representation that we can evaluate with numerical integration. So you might have heard about contour deformation in Stephen's talk. And you can think that this is already a solution and we can apply this right away and we're done. Actually, you can be smarter about it because you can analytically get rid of this I epsilon prescription in some ways. And this is something that also Herman Rodrigo started, which is referred to as loop tree duality. And the idea behind it is very simple. You start with this integral, and then you look where the singularities lie. You find that they lie on shell hyperboloids, one for each propagator. And because it's a quadratic denominator, you can factorize this denominator and you can parameterize each hyperboloid with the loop energy component. And like this, you just end up with a rational function. And integrating a rational function is very easy because we can just use the residue theorem for it. And for this, we just have to look at where the poles lie. So we can just project into this energy dimension, see where the poles lie, shift them according to the causal prescription, which is hidden here implicitly in these on-shell energies. And they make the poles shift like this. And now we can choose an energy integration contour. For example, we can close on the lower complex half plane. And like this, we know that the solution of the integral is just the sum of the 3 residues that lie within. And residues are nothing else but cut propagators. That's why we can represent it in this nice diagrammatic representation, where I added a sign to these cuts, which refer to the positive energy solution. In this case, we have a sum of 3 diagrams, and they're all set on shell. The cut propagators are set on shell with a positive energy solution. So like this, you might think that we already got rid of this causal prescription because it seems to be hidden here, but it's just implicit in these on-shell energies. But before that, let me just mention that this is actually also understood beyond one loop. For example, a 2-loop, it would look something like this, where there's a subtlety, which is that these cuts are not only performed with positive on-shell energies, but sometimes also negative on-shell energies. Yes. Exactly. The thing is, so this I was going to mention, you will end up at a different representation of your integrand. So when you write down all the terms, it will look different. But if you evaluate the whole thing at one point in integration loop momentum space, it will be the same thing. So it's locally the same thing. Yeah, the tree is just a diagrammatic representation in the end. I mean, it's a name that was given for the obvious reason that you cut as many propagators as you have loops. So you always end up in a diagrammatic representation that looks like this. So this is kind of what this is about. So these cuts you couldn't have because then you're left with a remaining loop. These cuts you also couldn't have. Yes, because you still integrate over the spatial components. Absolutely. And also, for example, for a 3-loop diagram, it would look something like this. And to make this more explicit, now it's just pictures, but in formulas, it would look like this, or at least that's how we write it in the paper. Just for some arbitrary loop integral with quadratic propagators, the loop tree duality would look like this equation, which is an integral only over the spatial loop momenta, and the sum over residues, and the sum is over loop momentum basis or spanning trees, is like an equivalent technical term. And then the residues, they're just your original integrand, and the cut propagators you just replace by 1/2 times the on-shell energy, and you evaluate the whole expression at your loop momenta, where the energies are set with respect to the right signs. That's kind of like this subtlety. There's no like closed form solution for this, but it's very easy to obtain this algorithmically. Yeah, this is not a unique representation. This is kind of what this thing is supposed to say, but that's not so important. Okay, so what do we do now? We want to integrate this loop tree duality representation. So we integrated out the on-shell energy integration already, but we still have these 3 remaining spatial components left for each loop momentum. And this is tricky because if we write down this expression, then we find we still have remaining singularities in the integrand. So for one particular case that I picked here, there are some singularities that appear pairwise. And this also appears pairwise, but some singularities just appear once. So there are hyperboloids and ellipsoid singularities. And if you want to understand where they come from, it's useful to take a step back to the 4-dimensional representation where we have these on-shell hyperboloids. And then we find that these new singularities in the loop tree duality expression, they originate from double poles of my original integrand. And in this case, the hyperboloids, they are because of intersections of 2 forward hyperboloids. So we have this picture. And then the causal prescription, this is now like an interesting point. The causal prescription makes these double poles, or these single poles that merge into double pole into the same complex half plane. And this is the reason why these singularities appear pairwise, and also why these singularities are eventually so-called spurious, like wrong singularities, so we can just forget about them. And these singularities, they can be a problem for numerical instabilities, for instance, if you want to evaluate this, because you have large cancellations, and you can explicitly remove it with a representation that we refer to as causal loop tree duality that William, who's unfortunately not here anymore, worked on quite a bit. And also, as you mentioned before, time order perturbation theory achieves an equivalent but different representation. There's also another cross-free family representation that was discovered recently. In either case, there are also these other singularities that are not spurious. They also appear from, they're also a consequence of double poles, but here from forward and backward hyperboloids. That explains why they look like ellipsoids. And in this case, these poles are shifted into opposite directions by the causal prescription. And that's why for vanishing causal prescription, they will pinch the on-shell energy integration, the energy integration contour, which is why only one of these residues will survive. So the surface only appears once and not pairwise. And these correspond to the genuine threshold singularities that we see. And we have to do something about this because they are just poles in the integration domain, and they need to be protected by the causal prescription. And then there are two ways to deal with this that I know of. One thing that we already heard about in Stephen's talk is contour deformation. I'm going to quickly repeat this as well. And there's an alternative approach of subtracting these threshold singularities. So the idea behind it is the following. So instead of having a function that is now that has a simple pole, we deform the contour around it, and then we can do a Monte Carlo integration along this contour. And now there are no more singularities, no more infinities in my integration domains, and this thing will converge. And an alternative approach to this would be to make use of this identity, or realize that an I epsilon prescription is nothing else but the principal value integration. And principal value means that you evaluate symmetrically around your pole. So if you did a Monte Carlo simulation that is symmetric around this pole, you will also find a converging integral. And again, another way to realize this would be to subtract the counter term that has vanishing principal value, and then the function would become smooth. And then you can do Monte Carlo integration over this thing, which is straightforward, and this will also converge. I will show these two approaches in the context of loop integrals now, but first I'll do the contour deformation. So if we have a single threshold singularity in our integration domain, then we have an ellipsoid, and the causal prescription would be this one. And if you want to realize this causal prescription with a contour deformation, we would require that the deformation vector has a positive projection onto the normal of this ellipsoid. So this would be a good deformation vector because it has a positive projection. This is also a good deformation vector for all these other thresholds that might be there. It would, however, not be a good deformation vector for a threshold like this, because now if we point down, this would not have a positive projection onto the normal of this pink guy anymore. In this case, we would have to add an additional direction, and we can weigh these directions appropriately so that they don't spoil each other's directions. And in the end, so like this, we have a valid direction for the contour deformation, but we also have to scale it appropriately so that we don't cross other branch cuts or go to other poles. And this is in general a tricky thing, and that we really have to watch out for. Although this is like an algorithmic thing that we solved. Nonetheless, to build a contour deformation, we have to find all these overlaps of ellipsoids in space, and this is in general a tricky mathematical problem. And there's the obvious drawback of contour deformation, that it's very hard to tweak these parameters to the right values so that this becomes an efficient integration. This is what it would look like for a simple one-loop box diagram along this line. So these are 4 thresholds, and we have a line here that we plot here. And you see that the integrand is highly oscillating, so this is certainly not the best approach to do numerical integration for. So the other approach that I believe is more stable is this subtraction of threshold singularities. And the idea is very simple. Let's just say we have an integrand with only a single threshold, then the integration domain would look something like this. And then we can turn this into a one-dimensional problem by just going to spherical coordinates. Then we can pick a direction, and along this direction, the integrand just has a simple pole. And we can find the position of this pole either analytically or numerically. And then we know that the integrand locally will just look like this. So to a first expansion, we find that the singular behavior is just a residue over a simple pole. And this behavior gives you a concrete prescription on how to build a counter term, how to remove this singularity. So you just build your counter term from this first order expanded term, and then you subtract it from your integrand, and you have no more singularities to worry about. Of course, you have to integrate the counter term back though. And this is easy because the principal value is just 0 by construction. So you're only left with the integrated counter term, which is just the residue that you already have in the numerator here. So the final expression would look something like this, that the real part of the integral is the loop G-duality expression, or everything that's equivalent to it, minus these counter terms. And the imaginary part would just be the sum of residues. So this equation does not look particularly appealing itself, but if you remember that residues are nothing else but cut propagators, oh, and this is straightforward to generalize to n loops. And now this imaginary part can be written diagrammatically, and diagrammatically it would result in this equation. And if you see this equation, it should remind you of the optical theorem. So a consequence of this approach is that you find a locally finite expression of this generalized optical theorem in this imaginary part. So what does that mean concretely? So if you wanted to find this representation, we just start with our, for example, forward scattering diagram or whatever loop integral that we look at. We can get the LTD representation, and then we can just get the imaginary part by going through each of these terms, see if a threshold is in there. We can parameterize it with our radial parametrization and extract the residue. And then it would correspond to this cut. And this cut, you see, also appears as this Katkovsky cut, where the loop is now cut as well. And you can go through each of these terms, and you see that just the Katkovsky cuts that you're already familiar with from the optical theorem, they just reappear in this procedure. Some don't have a threshold at all, but some others have multiple thresholds and so on. But in this way, you actually can systematically generate all these terms from the optical theorem. And the key point here is really that they are all parametrized in a maybe weird parametrization, but this weird parametrization makes sure that all singularities or all singular regions, in particular also infrared singular regions, are now aligned, and they will locally cancel in the sum of all these terms. And there is a caveat to this, which is that it heavily depends on the radial parametrization that I choose, because when I choose a radial parametrization, I have to pick an origin, and this approach depends on where I pick this origin. I will illustrate this in a minute. But to see how this local cancellation works, let me show this equation for the real part. So here I have singularities at first. I remove the counter terms, and the integrand becomes flat. And for the imaginary part, it's interesting because we have here an intersection of two thresholds, and the residues, they will individually blow up. But if I sum them up in the same parametrization, they will locally cancel this divergence. And I end up with a flat integrand that is trivial to integrate numerically. And this cancellation I can break. So like this, it's not broken. Here it's all flat. But if I put my origin outside of the overlap of the ellipse, in this case, I can break the local cancellation here. The reason is basically that I invert the orientation of my parametrization of the thresholds on this dark blue line. And So the solution would be, I just put my radial parametrization inside the overlap of these ellipsoids, but this is not always possible. In particular, in this case, this would be a threshold configuration of a box diagram. And here you see we have a bunch of overlaps. And one straightforward solution to this would be like a multi-channeling approach. You can just multiply the integrand with 1, basically, and then you divide the integrands into different pieces. And like this, you can separate it. You have one piece with a single overlap alone, and you can use this method on it. This is a method that works, but I think it's not the end of the story because there are many properties of these overlaps that can be exploited. For instance, it would also be fine to just put my origin here. I'm not going to go into details why, but this would also be possible. All the cancellations would be aligned. And there are some other properties of these intersections that could be exploited to kind of simplify this procedure further. This is just a quick comparison of threshold subtraction and contour deformation. This is a pentagon integral with a bunch of thresholds. The red line would be a contour deformation, would be the integrand after contour deformation with a scaling of 10, scaling of 3. So a smaller contour deformation would result in an even more oscillating integrand. And the larger deformation, which is not always possible, would result in a flatter integrand. But nothing is as flat as just subtracting the thresholds right away, which would be the blue line. Also to illustrate the stability of this approach, I integrated a one-loop integral with 30 legs. This works well with a couple of thresholds, but also with a lot of thresholds. And I get a below 1% accuracy with, what was it, like 1 billion Monte Carlo samples. I should wrap up. And but before, I want to also show something that's actually relevant, which is now the numerical integration of scattering amplitudes. So why are we doing this? In the end, we want to integrate two-loop scattering amplitudes. And the approach that I'm following here is in collaboration with my former group in Zurich, where we use explicit infrared counterterms that have a nice factorization property that remove all these infrared singularities locally from my loop integrals. And we use UV counterterms based on the BPHZ forest. And then, for instance, for a 2-to-2 amplitude, forget about this third photon for a second, then the one loop amplitude would simply look like this. We have just a few diagrams. Then we have an infrared counterterm, and then we have a bunch of UV counterterms. And this thing I can, for instance, integrate with this method. And here's a plot of a bunch of these 2-to-2. So there's one 2-to-2 amplitude, real and imaginary part, with massless photons. Then this red configuration is with massive photons. And the blue configuration, which is for a 2-to-3 process with massless final states. And only for the massless 2-to-2, I had a benchmark available. So that's why there's only like one comparison to the analytic result. And this is the Monte Carlo error in percent. And don't worry about this 100% error here, because this is only because I'm crossing 0. And of course, it's very difficult to integrate 0 with Monte Carlo. So the error is expected to be of the same order. And now first applications to two-loop amplitude. So this is not the whole two-loop amplitude for this process, just the NF contribution, where you just insert a fermion bubble into the gluon propagator. And then also in this case, we managed to integrate this numerically for 2 massless final states, 2 massive final states, and also 3 massless final states. And our next goal will be to go to 3 massive final states, which is of course very difficult already because now we have a 5-point two-loop amplitude with many scales. So I don't actually know whether this is known analytically. But in this case, where we have 3 massive final states, the threshold structure becomes more complicated. So then in principle, we also have to use this multi-channeling that I mentioned before. And with this, let me come to the conclusion. So with everything I showed you, loop tree duality and this threshold subtraction approach, this should have given some kind of insight on all the cancellation mechanisms that are like hidden within an amplitude calculation. And I think this is really interesting because it's some physical cancellation mechanism. And exploiting this, we can integrate these expressions numerically. So with loop tree duality, we first get a convenient threshold structure. We go away from these on-shell hyperboloids that extend to infinity to confined regions, these ellipsoids. That makes the treatment much simpler right away. And with the threshold subtraction, we get a flat integrand. We don't have to use contour deformation and the parameters that come with it. And we even get access to this locally finite optical theorem, which eventually we can exploit to get to make calculations of differential cross sections where the infrared singularities are explicitly locally cancelled. So you don't have to worry about any infrared regulating schemes. And but yeah, for this differential cross section calculation, there's a lot of extension and improvements necessary. But as I showed you before, now that we're already tackling 2 loop amplitudes, so I believe that soon we'll have some significant results already about this. So yeah, with this, I want to thank you for your attention and welcome any questions. Thanks.
I just wonder whether anyone working on these things has thought about using, instead of the doing the poles in the time component, zero component of momentum, using a light cone component where the light cone vector may be determined by any or even several, depending on the massless external legs. So that at first sight looks more convenient for the usual high energy scattering. Also at first sight looks simpler because propagators are linear. Okay, it's not really true because you don't know on which side of the complex plane this lies because it depends on the other light cone component. But anyway, the question is, has this been pursued, and does anyone know?
So I personally have not pursued this. I know that Eric Lanen with collaborators, they have looked into something like time order perturbation theory in position space, where they don't go to light cone coordinates, but that's in position space. So maybe there's some overlap there. And I think a couple of years ago, I also came across a paper by George Sturman where I think he was investigating something similar, but I couldn't say more about it. But maybe you know.
No, indeed, I mean, you can. What is relevant here is that you integrate 1 degree of freedom per loop. So this is the simplest version because you integrate the energy component, and this is convenient because then the remaining integration domain is Euclidean, 3 momentum. But indeed, you can integrate any of the component of the loop. So indeed, we have several. We have presented expressions where there is a general. It is generalized to any coordinate system. So it is. What is relevant here is that you integrate 1 degree of freedom per loop in order to open the loop to the. No, but if you look into our paper of 2008, you will have some explicit results for light cone coordinates. No. You can do it. So it's a question of time.
I mean, one obstacle that I see is if you have linear propagators, then everything changes, of course, because having these poles on one side of the contour always is follows from having quadratic propagators. And then I don't know whether the same identity would come out or if you have to jump. Yeah, it could be something interesting to investigate.
Just one comment, because we also introduced the local subtraction of infrared and ultraviolet singularities within this framework.
Yes.
Okay, it's just a comment. Okay.
Okay. Can we go back to this kind of nice cutting stuff where you cut, etc.? The graphs cut, this kind, yes. So you saw before some of them they were corresponding to some Katkowski cut, but some other not.
Oh, this.
Where was this? Sorry about that.
Oh, and this will take a while. I'm sorry.
Okay. It takes them.
So this.
Yeah. So there were some where we have a cross. What it means that? It means that you forget them or what?
So this is one term in the loop tree duality representation. You look at it and you just see it doesn't have any denominator that can vanish. It doesn't have a threshold in there.
So therefore,
there's just no residue that survives because it doesn't have any.
So therefore, they don't contribute to the imaginary part or what?
Yes.
Okay. And I mean, okay. In my mind, there is an issue. I mean, how to get in, let's say, a double in a pentabox, for instance, or in an hexabox, how to get the imaginary part of this guy. I mean, we get it, but okay. Everybody uses basically something which is correlated between us. I'm wondering, is there any independent way of calculating with your method the imaginary part of a hexabox? Can you do that?
I think so. I still have to integrate over the unit vector, basically. So I can't promise you a very precise result, but it's possible.
Okay.
So I want to ask something similar. So do you have sort of a diagrammatic representation for this, what you call threshold singularities, for the residues?
Mm-hmm.
I mean, you have a diagram on the left, let's say. Can you write sort of all things that you need to subtract in such a way that you have some simpler diagrams, which will be kind of residues, and then some sort of fake diagrams whose discontinuity will be exactly what you need to subtract?
So you mean here, so this LTD expression is basically a sum of diagrams, and then the counter terms?
Yes, so I mean, in a way, what you're trying to subtract is the imaginary part.
Yes.
Right? Imaginary part is defined at the level of diagrams. I take a diagram, I cut it in a few places.
Right, it's like these diagrams.
So this doesn't need to have any particular parameterization.
Yes.
So does this formula sort of, do you know this formula? Does it exist?
So in principle,
well, in principle,
I mean, okay. The thing is, I could write it down just as the imaginary part, all these diagrams divided by my arbitrary parameterization R minus R star. But this is not physical. This diagram is physical, but then the counter term itself is not physical, and I only construct it in a way so that it integrates to 0. And there are many ways to construct it. So one could also leave the original threshold in there, which is this surface, and that would make it.
Counter term is, I mean, take this diagram that is now sort of in the shaded area to the left, right? The second line, the leftmost diagram.
This.
No. This one, yeah.
Yeah.
So you have two propagators cut, and then you have a loop, right? So the loop is on the Marshall, it's basically a number. Okay, and then the imaginary part of this thing, you know, of these two propagators is the imaginary part of a one loop bubble. So, I mean,
I mean,
It's a physical representation of this particular contribution to the imaginary part, right?
what I'm trying to say is, so this equation for the real part, another way to write it would just write in front of it PV of this integrand and remove the counter term altogether. This is a trick to evaluate the principal value. But so the physical thing is, it's the principal value of my loop tree duality integrand. What this principal value means for more higher dimensional integrands, I don't know. I just know that like this, I can realize it properly. So this thing, and I mean, this is constructed with all these, like from the imaginary part, basically. But then the imaginary part is physical again, but these counter terms are just kind of some.
What is that here?
What is what?
And
The number of loops.
so in 2 loops you have n equals 2.
Yes.
Okay, any other urgent questions or? No? Okay, let's thank Dario again. Thank you very much. And please wait a moment before you leave. Martin would like to share something with us. Thank you.
I just, no, okay. For 15 or almost 20 years, we have this postdoc deadline agreement that no one forces postdoc applicants to take a decision before January 6th. Now, everyone now understands how inconvenient this date is, both for the applicants and also for us who have to go through the applications and maybe have interviews and email exchanges over Christmas and New Year. So a group of people has made an initiative to move this date to February 15th. And I'd like to sort of advertise this a bit. Probably many of you know already, but some may not. And so I just want to mention this. And actually, maybe Dario, I wasn't prepared. Do you have access to Google and could just Google for postdoc deadline agreement? Because there's a website where you can sign for your institution or the representative of your theory group. And so the idea is that this could go into effect already for the next year's applications, meaning this year's or then next year's, provided a certain number of institutions signs or ratifies this agreement before September 30, right? By essentially sending an email or posting something through this website. What do you get?
What should I?
Maybe someone knows. I didn't bring a computer. That's okay. So let me just inform you. I think it's just a question whether you like it or not. I strongly encourage. Also, there's another reason that there's more and more overlap with the astrophysics cosmology community, and their postdoc deadline agreement all the time has been on February 15th, right? And so this would synchronize it, and it would basically mean that, answering your question, postdocs have to send out their applications only after Christmas, and everything's postponed, right? So no, the hiring will still be 1st of October, the usual thing. So okay, it's a good coffee topic, but I just want to make you aware of this and also of this September 30 deadline for ratification. So of course you'd have to discuss it with other members of your groups. If you're interested, please do. There should also be somewhere a list of institutions that already signed. I know that some of you have already signed it. Let's see. Where did you find this? GitHub is fine. Maybe go down. There's an instruction somewhere. No, there's a long list. Last time I checked, it was something like 80 institutions already. Okay, what about emailers? The new account can be found here. Maybe you check that one. Or second line, yeah. Okay, that's not the web page how it looks to me. But anyway, so let's stop now and you may take a look. It's the old one that you're looking. No, these are the people who. No, here. Yeah, exactly. That's a list. So I mean, you understand that this works only if there is somehow a worldwide agreement, because if you shift the deadline to a later date, I mean, there should be some agreement, because otherwise people, that was the problem in the past, were making offers earlier and earlier to somehow fish away the best postdocs. I mean, this shouldn't happen. And so therefore it's important that many people sign and agree to commit to this agreement.
Thank you. See you at coffee. I'm sorry.
You signed already. First sign. Criterion. Their measures. I think they said somewhere they want 100. This has been reached. Slides of email list of the so any other way to reach the call? Actually,
That's sorry.